Welcome, everyone. Thank you for joining us today. My name is Odette Hines, and I'll be your moderator for the webinar entitled 2020 Year of Depth, featuring existing technologies, opening the perspectives. Your presenters today will be Miro Mlejnek, who is Technical Sales Manager at EMEA at Intel, and Ferdinand Reitze, Product Manager at Framos. Before we start today, I want to provide you with a few housekeeping rules. All attendees are in listen-only mode. If you have questions during the webinar, please type them in the question section in your GoToWebinar control panel, and I'll ensure that they're answered at the end of the webinar. If we do not get to your questions today, we'll send the answers to you a few days after the webinar. The on-demand version of the webinar will be available within the next few days. We'll ensure that that is sent to you as well. If you require a conversation or a demo, please ensure that you put that request in the question section of your GoToWebinar control panel, and I'll ensure that they're directed to the presenters at the end of the webinar. Now, without further ado, I'll turn it over to Miro.
Thank you very much, Odette, for a very nice introduction. I'm very pleased and privileged today being on our Framos Meet-Day webinar. My name is Miro Mlejnek, and I'll be talking today about the physical principles of Intel RealSense depth cameras and all the processes behind how we perceiving the depth and what is good in it for your potential businesses. At the beginning, very short legal disclaimer. We just need to be sure that our cameras are not targeted for mission critical systems or some applications which may be harming the health or life of a human. And now let me go to our technical content. So why is 3D vision important? 3D depth cameras providing specific information what 2D camera is not capable to do it. And this is the information that you can read out from the particular pixels in a frame on the field of a view, the distance of a pixel from the camera sensor. Yeah, so it helps you to understand shapes, size of the objects, distances, and the system considering also perception of the depth is much better performing in understanding of the context of a scene in general. Yeah, so 3D vision is a very booming technology, and even for Intel is a very important technology for our further growth and adoption of new technology features in our product development. As you can see, I selected a specific slide just to show you why is 3D important. And it's pretty easy in a 2D vision create some optical illusions when you fully relying on the RGB stream. You may be challenged if you're spotting the bunch of lookalike objects, being crowded somewhere in the particular areas, objects with the same color, and then it's very hard to perform any segmentation of the objects, distinguish how many are there, and etc., etc. And depth information can precisely reveal some hidden information which may not be visible in the RGB and help you in a better understanding of the context of the scene. So like in this picture, these two slides, you see set of 6 dummies standing on the stairs. So for RGB, it's very challenging to spot and understand what it is. Your brain maybe is trying to, whisper to you like, oh, it's probably, shape of a human. I can see the head on the top of the stairs, but you're just judging. But our camera, if you look in the same object, can precisely reveal how many is standing on the stairs, and also calculate precisely their distance from the camera. How to use this technology? So these technologies are typically used as we see on our structure of our customers, and these joint projects we're running with the Framos company. They are related mainly to object measurements. So standard volumetric, scenarios like measuring the size of the box, measuring volumetric features of the objects. Second scenarios typically used for depth cameras is obstacle detection and collision avoidance. So in a moment you're building some autonomously moving device like robot or drone, you need to understand what is the context of the scene in terms of the distance of the particular objects from the camera, and depth vision is helping you to assign such numbers and mitigate potential collision throughout your journey in a crowded area. And the last one is object recognition. So perception of the depth is helping you in the segmentation of the objects, and also is bringing these features related to the 3D features of the object. So will be different if RGB camera will not be capable to distinguish between white circle and white ball. Our camera can do that. Yeah, so you can spot that this second object is coming with the spheric features. Yeah, here's a 3D, and this is an example ball, not the white circle. So these are the main scenario where typically clients are using depth cameras to reveal specific information which may be challenging for standard RGB or other vision channels. So if you're looking in the general, the main verticals, you can see InterRealSense and Framos solutions are falling into these 5 major segments. It's a face identification, robotics, 3D scanning, measurement logistic, and recognition and interaction. Face identification, you may be a little bit confused maybe why depth camera is used for face identification. If you're thinking about the process of a face identification, how algorithm is running, camera first of all need to prove that no one is trying to spoof the system. So there's no picture exposed to the camera. There's a real face of a human. So depth camera can reveal the 3D structure of a human face and prove, yeah, this is a real human looking to the camera. And then I can go for another step, grab the RGB channel and run the biometrics for face identification. Robotics, this is related to this mitigation of a potential, collisions with the objects. 3D scanning, there's plenty of scenarios how you can utilize it in the marketing, scanning your products for sale. Some companies using 3D scanning for inspection of the construction processes. So there's plenty of scenarios. Measurement and logistics, this is related mainly to logistic services again. So typically customers like, Deutsche Post, FedEx, I don't know, DHL, they may benefit from such solution because this is, speeding up the process of the processing of a parcel from the acceptance to dispatching to the final destination. And recognition and interaction, especially now under the COVID-19 threat, is a big thing that you can combine various technologies like crowd management, counting people in the particular areas, measuring the flow of the people in a certain areas, and also trying to spot and run the distant fever metering. This all is possible to, thanks to technology when you're revealing the depth from the scene. So now let me talk about the principles, how cameras are working. I think this is very important to understand what you can expect from the particular technology, because we learn over the time that it's not possible to create ultimate 3D camera. Every camera has a certain advantages, certain limitations. And first of all, when you're starting with the selection of a camera in the 3D vision, you need to be absolutely clear about your usage model, scenario, and light conditions. And then you can go and pick the right camera and maybe tune it a little bit to improve your expected, results. But again, you need to start first of all with the right scenario and assignment of the technology to the scenario. Yeah, it doesn't work like I will pick some camera randomly, just learning this is a 3D and expecting that you will get a super service, because there might be some limitations. Now we're talking about them from the physical principles. What is the potential benefit or negative impact to usage of the certain technologies under certain usage models? Before I will start, I will just to highlight how you should understand the method, how we're developing our cameras and computer vision systems at Intel in the RealSense group. The reason I'm running on the slide the profile of a human head is very simple. We're literally mimicking the functions of a human head. We believe that especially in the depth vision, nature did very robust solution for vision, which is obviously stereo. You will never see on the planet animal with the one eye only. Yeah, so there are two eyes or more eyes in the case of an insect. So this is a proven technology thanks to its robustness. You know, this is a winning story. And on the slide, I just like to highlight that our sensor is not bringing you any intelligence or smartness. This is just a sensor telling me the distance of the pixels, you know, from the camera. And so the intelligence must be driven by some other device like high performing PC or visual processing unit processing the data and telling you what's up. But our camera, again, is just the sensor, you know, sensing the depth, providing the depth stream, or optional also depth stream plus RGB stream. Yeah, so you should see our cameras as a human eyes. Yeah, and they must be connected again in a connection with the brain. And the front part of the human brain is actually really the place where is stored your algorithm managing the consensus of a disparity shift, which is the algorithm, you know, human brain is using for perception of a depth. And we're running something very similar. We also do complementary tracking, motion tracking sensors. So they are literally mimicking the function of an inner ear in a human head. So you can inject the depth stream with the 6 degrees of information from the motion sensor. So for someone who is making the drone or the robots, he can combine our camera with the motion tracking sensor and can achieve very good results in terms of understanding the positioning, maybe up to top level solution like optimized SLAM solution for robotics. And then you see that in the hypothalamus of a human brain, there's a visual processing unit called Movidius, or it might be PC in your understanding. And this is something which is processing all the data from the sensors, from the motion controller, from the RealSense camera. And here you're running the logic of understanding. Yeah. So literally, if we're creating this product, we do our best to make them very complementary, yeah, to enable them to fly together. And we're starting from the sensing. If I'm sending the physical values, it brings me the option that I can understand the scene if I'm running obviously proper algorithms, yeah. And if I have enough of information, and then I'm an example, I'm the robot, and I need to decide to make some action, and I'm deciding with my interaction, then I can do it because I have enough of data, yeah. And over the time, you're storing the data, you see how you're performing against the reality with your system. So you can learn out of this data, you can improve your algorithm on fly. Yeah. So this is just the intro slide, just to give you the, you know, the stage understanding, you know, how we're thinking inside of Intel, you know, how we're creating new products, and where we bring this, you know, complementary collaboration between particular specific parts, you know, to orchestrate more complex devices like, for example, you know, robotic system or drone system to deliver expected service. So this slide is starting to talk what technologies we're using at the moment. I believe that Intel is at the moment the only company providing a depth vision based on 3 different technologies or physical principles. So we providing cameras based on a coded light, or AKA structured light. It stands the same. We have a camera based on a stereo matching, and we also have a camera class of a LiDAR based on the time of flight technology. And again, as I mentioned at the beginning, the reason behind is that it's not possible to create ultimate camera to make everyone happy. Yeah, someone is looking after precision, someone is looking for operations indoors, someone like to have a robust system operating on the sunlight, in the darkness, or combination of both. And then is coming the challenge, what camera will serve the best. Yeah, so that's why we have these 3 distinguished technologies to address the market. 2 technologies, coded structured light and stereo, are based on a triangulation. And this is definitely known to you. So triangulation is based that you know the baseline between the laser projector and the infrared sensor, or between left and right eye in the case of the stereo camera. And if you know this distance, if you know the focal length of the sensor, and you know, for example, in the case of the structured light, the spatial structured light patterns processing over the time. You can calculate the distance of a particular pixel in front of the system. LiDAR is a different story. It's based on the time of flight technology, so speed of light is constant value, and system is measuring the shift between the projected flash of a light and incoming flash of a light, and just playing calculation utilizing the Doppler effect will tell you exactly the distance of the object from the camera. And every technology is coming with some superlative features, very positive for certain scenario, and sometimes maybe failing because especially light conditions. So coded light cameras, they are based on a heterogeneous, highly intensive laser projector. They are optimized because of the human eye safety. They are optimized for measuring the distances between 0 to max 1.5 meter, under very good light conditions. Typically, the operational range of the structured light camera is between 0 to 1 to 2 meter. Again, depends on the light of ambient light intensity in the area. They are very precise, and you can see coded structured light cameras typically as a security fashion identification systems in the airports, access systems. Companies in the healthcare, they're also using coded light cameras for close-up scanning and a 3D modeling of, let's say, bodily human parts, for checking pre and after surgery process of the healing. So if someone is benefiting from the precision and the close-up, and is using only one camera in a particular scenario, he's happy with the coded light technology. These cameras are relatively not expensive, so this is like entry-level solution for someone who would like to start with the depth solution, but limitations are significant, especially in a distance operation. So again, it's just for close-up, because also using the structured light, you can have only one camera looking at the object, because otherwise will be happening, interfering between two signals, and system will not be capable to read out the information. In the middle is the stereo. So I mentioned this is the most robust technology you can use at the moment. In our case, stereo is definitely doing probably well over 70% of the business, and this is because of its robustness. Last one, LiDAR, time of flight, is a relatively new technology for us in Intel. We finished the development last year. We launched L500 family in the Q1, and the first shipments are expected a couple of weeks from now, starting in June. So LiDAR will be a very interesting solution for someone who is running scenario under control light conditions, strictly indoors, and is really benefiting from the high precision. I mentioned that we have also this tracking solution, so they are complementary to all three families of the products. I will not talk about them today because this is not related to the computerized vision. These are just the accelerometers and gyros, but can be complementary used with our cameras. Some of our cameras actually are also coming with us tracking microcontrollers inside. So you just need to properly pick up the right product and talk with Framos engineering what will be the best solution for your development. So this is just the introduction slide, and I will talk in more details about the particular technologies, how it works, and what are the benefits, and then also some counterproductive features you need to be aware of, and then if you know that, you can pick up the right product. So what is coded light? So coded light, or structured light, aka it stands the same, is a projection of known patterns onto the scene, and evaluation how these patterns they're forming on the surfaces in a 3D. These patterns might be parallel stripes, like in our case, we're projecting the parallel stripes. Other solutions might be based on bullseye circles. So basically something as a geometrical pattern, and by analyzing these deformations of the patterns, vision processor inside of our camera is calculating the depth and surface information of the scene. This is one of the reasons why these cameras are an example heavily used in a fashion identification so far, because this camera is absolutely perfect in a precise anti-spoofing features and functions. Yeah, so you can't, you know, use picture of someone and bridge the system, because camera will immediately identify that this is not a 3D object. Yeah, so so the laser, infrared laser projector is illuminating set of a predefined spatial frequency coded IR vertical bar patterns. Yeah, and this is slightly moving over the object. Yeah, that these are warped by the scene, reflecting back, you know, bouncing back to the infrared sensor, to the camera, and then camera is then evaluating the pixel values. Yeah, the camera is looking what is a black and what is a white. Yeah, and then is using these alternations to generate the particular depth frame and putting them together and creating the continuous video stream, which is transmitted over USB to your host. Yeah. So if you're considering how is it running, again, you can have only one camera looking particular object. If you have two cameras, they will interfere. You need to be careful that object is not flooded by sunlight or by another strong over infrared radiation. Yeah. The camera is using 860 nanometer spectrum of infrared laser. So if face of a person will be flooded by sunlight on the direct sunshine or being outdoors, system will probably fail. Yeah, and especially in the bigger distances, like let's say 70, 80 centimeters, 1 meter, will not be capable to operate. Yeah, so this technology is a very good, precise, very robust, but targeting indoors usage. I'm talking about the ASIC inside of the camera. So interesting feature of our camera is that the whole processing of the creation of a depth is made up by specific dedicated ASIC. We call it VPU, Visual Processing Unit. And this ASIC is processing the whole algorithm to generate the depth stream. So you can be sure that our camera is never causing any payloads to the host. Yeah, so our systems, not just coded light, structured light, but all cameras we do as a structured light, coded light, stereo, and LiDAR, they processing the vision in the depth through the ASIC. So they're just sending passively the data. So you'll tell to camera what format you're looking for, what resolution, what clipping rate. Camera is feeding your system with the data and is not causing any payload to the system. So it's valid for all our products. If you're thinking what I need to use for camera I'm developing together with the Framos, the answer is you need to talk with your software engineers and they will tell you how much of a processing computational power you need for your post-processing activities. Yeah, but again, you're not doing anything related to the creation of a depth stream. This is done by camera, and this is one of the biggest advantages of our system, because our system is not, you know, computing power hungry. So it just is all made up by camera and sent to the host. So if I switch to stereo matching, I mentioned is the most robust technology, really proven by Darwinian theory of evolution of the species. Stereo matching camera you can look into the sun, and you can flip your camera, look into the dark tunnel, and camera will immediately accommodate to the different gradient changes in the light conditions and will operate again. Yeah. The biggest challenge for laser-based system is a sunlight radiation. So this is always very challenging, and because camera must be, you know, certified as a, you know, human eye certified protective device, you can play with the unlimited laser power. Yeah, so our cameras we do at Intel must be certified for human eye safety. So that's why I can't create a camera capable to operate outdoors on the sunlight with unlimited laser performance and damage someone's eyes. So that's why we rather implementing and improving the algorithm of stereoscopic matching vision, because this is very robust and can operate under any light condition. And there's no laser source in this camera, which will be potentially harming the sight of a human. Stereo matching camera, the principle of operation is that camera must be capable to see diverse environment. Yeah. So if your environment will be like very poor on a visual information, like let's say imagine like you're driving the car in a fog, Yeah, so your brain is not capable to receive from your eyes any visual information. So then your brain can't process any understanding what's up, where I am, what is my speed, where I'm heading. Yeah, because everything is a foamy, milky, and you're not capable to get any visual information. Yeah, same analogy might be scuba diving. You know, if you're in a certain depth under the water, under sea, and a certain moment you don't know if you're swimming up and down because everything is look-alike. Any direction you look is the same. Yeah, so if you like to use a stereo, you must be sure that there's something visible for camera. Yeah, so the scene must be diverse. If you're using cameras for something like drones or robots and they're operating outdoors, nature and the exteriors are very diverse. You know, so camera can always see something and is performing very well, can deliver always to expectations. But there might be some specific challenges like indoors. For example, we'll be building the robot, and robot will be approaching white wall, and there will be no any structure on the wall. Wall will be strictly monocolored. Then system may be, you know, suffering how to calculate the distance because he can't spot any correlation as a pixels to calculate his distance. Yeah, and we mitigated this problem that we have a small laser projector who is projecting faint random dots, yeah, to the plain unstructured objects. So he's actually adding extra diversity information. And ASIC inside of the camera, he thinks like, wow, there's something like wallpaper on the wall, there's something painted on the boxes, and then it helps drastically to improve the vision in a 3D. So we're literally adding something like extra contrast. Yeah, the camera can see it, can see these pixels, and it will use them to calculate utilizing disparity shift algorithm the distance of the object. So I put the 3 photos, and you can see on the top one, you see this plastic trays in a shelf. And the first slide is using that camera is in a passive mode, so no laser is active. And if I'm running this mode as a passive stereo camera, you can see that everything what is coming without any structure or any other visual information, you see on the bottom, the very bottom left picture, it's dark. So this is the moment when I can assign any gradient of a color because I don't know the distance. Yeah? But in a moment, I will illuminate the same scene with this laser projected light. The noise is gone, and I can see beautifully the details and the distances of these objects. And I will show it in a demo. So how this ASIC is running inside. So camera is coming with the 2 eyes, left and right eye. We have, by the way, 2 types of cameras. We have a rolling shutter and a global shutter. So in the moment you're considering robotics, dynamic movement in a scene, go for global shutter. The electronics inside is the same, just the difference is the feature of the images. So what system is doing? So ASIC is processing left and right vision frame, and in the first instance, he's cleansing the noise from the CMOS imager. And so he's breaking down the frames into small tiles, and he's looking for look-alike patterns, you know, on the left and right eye, you know, tile by tile. An example, if he's spotting in one section white pixel and he can't spot the same pixel in an alternative field of view in the other eye, he's taking consensus to eliminate it as a noise. And then he's sending to the ASIC for processing over depth clean frames. And then ASIC is running along the epipolar lane. He's looking these 9 pixel areas, and he's looking for similarities. So in a moment, he's noticing that, for example, this bitmap on the very right side is the same one like this one in the reference image on the left eye. So you can see that the bitmap is exactly the same. He's starting to calculate its shift in the pixels. Yeah. So he's starting to calculate in the pixels the value called the disparity shift. And then if you know the camera baseline and you know your focal length of your optical system, you can calculate the distance of this particular tile with this specific bitmap. Yeah. For someone who is interested how algorithm is running, so this is a little bit simplified. Yeah. So if you're using the sum of square differences, for block matching algorithm, there are some fixed values. So for example, lens focal length, 942 pixels, baseline, roughly 55 pixels. So if you're looking at how we're converting this disparity shift into the depth, here is the formula. So baseline times focal length divided by disparity shifts tells me the distance in the millimeters of the object. So this is the elementary formula, you know, to converting the disparity shift with the knowledge of my baseline and the focal length into the distance in the millimeters. Yeah. So this is how stereoscopic camera is running. You can control lots of the features. I will show you in a very short demo how is it running. And this is what is the devil in the box for the stereo camera. I mentioned that we have a passive and active stereo camera, so it means that if you're building again something like the robotic system, and or in your future solution you are not sure about the light conditions, and you are worried that camera may be exposed to some look-alike unstructured monocolored object, pick the camera with this small laser projector and as an active stereo camera. And in the case of this specific scenario, you can kick the laser on, and then you can benefit from this, let's say, artificial fake structure projected by laser to help you to mitigate the problem with the unstructured objects. Yeah. So passive stereo is always perfect for operations outdoors, outside. And you will be probably challenged in the darkness, because there's nothing visible. So if you see nothing, camera can process the depth. If you have active stereo, it can work obviously outside because sunlight is anyway overwhelming this radiation from the laser. Will probably not work well on a material which is absorbing IR. So if you have something like dark matte object or something like loads of water in it which is absorbing the IR, this may be the challenge. Yeah, but can help you with the works in the dark, because this is adding the visual information on the dark object and you can calculate the distance. So this is just the benefit summarizing passive versus active stereo cameras. So drone, passive. And if you're building the robot who will be operating indoors and outdoors, go for active camera, because you may be benefiting when robot will be facing, I don't know, plane door, plane surface, and you need to understand its distance. So this is in a nutshell, very briefly, how stereo camera is running. Few conclusions. There are also some inevitable feature of a stereo. So stereo is very sensitive to calibration. So you need to be sure that your camera is properly calibrated. Yeah. You need to check the calibration of a camera, especially after some massive mechanical or thermal shocks. Yeah. So if there's any mechanical thermal stressing, it's probably good to invest a little bit of your time to check if the calibration is fine. It takes a few seconds. And in our ASIC, we have a special IP block. You can call for help and check if your camera is running healthy vision or you need to run calibration. And recalibrate camera takes max 5 seconds, typically less than a second. Yeah. So calibration is important. Second bit is the error over the distance. So the stereo cameras can be used for super precise 3D scanning. Yeah. So do not expect anything like millimeter precision, etc. This is obviously not possible. Stereo camera, if you're looking, for example, our data sheets, the root mean square value, the RMS noise, let's say in a 2 meters distance, is about 2% of imprecision. So 2% from 2 meters are 4 centimeters. So if your object will be like 2 centimeters, between 2 to 4 centimeters and smaller, you may be below the threshold to be visible by camera over this distance. Yeah. So it depends on the type of a camera. We have plenty of camera with a different baseline. So if you'd like to have a better precision over distance, you need to have a camera with a bigger baseline, because you have a bigger base for triangulation. Yeah. But if you have a big baseline, camera is less sensitive for close-up measurements. So for example, min Z distance for our standard camera is roughly 30 centimeters, yeah, depending on the exact model. Yeah. So min z distance is also a function of the resolution. So if you decrease the resolution, you can also decrease the min z distance. But especially in the robotics, some customers, they like to have a very close-up capabilities in a 3D vision, and this might be a challenge for stereo. And so basically these two things, as precision over the distance is actually anabolic problem, and the calibration. These are two things you need to consider in your preparations in your design. So now let me talk about last technology, and this is LiDAR. So our LiDAR is based on a micro electromechanical solution. There's a small mirror, so we really making a solid state LiDAR based on an oscillating mirror inside. So how is it running? So forget about the 2D LiDARs like other companies are doing, spinning on the roof of the car. It's not a 3D LiDAR. Our LiDAR is a truly 3D solution. Yeah? And the principle is that if I will attach the power to the system, the laser mirror will oscillate along the x-axis. So you see that this oscillation up and down. And then behind the mirror, I have a piezoelectric crystals, and I can control the angle of the mirror along the y-axis. And so if I will kick the system, mirror will start to oscillate, and I will control how mirror is moving from left to the right side. It will create this pattern, how the light how the beam of the light will travel in the field of view. So in the moment I will start to measure with the ASIC inside the time of travel, I can assign to these pixels its distance. Yeah, and after a few iterations, I can reveal the whole 3D image of a scene. I will show it in a demo. LiDAR is probably our most precise camera at the moment we have, but remember, this is for indoor usage. And consider also physical features. So if you have a matte black objects in a certain distances, may not be visible for LiDAR. And LiDAR also must be human eye safe device. So we have a special chip inside the LiDAR who is on the fly controlling the intensity of the laser. So if, for example, my LiDAR will be facing the wall 8 meters away, I can measure the distance of the wall 8 meters away. But if there will be something passing in the trajectory of the light, as the object might be, for example, the head of a human, the laser will immediately notice that, and he will minimize the laser performance to be in a correlation with the distance of the object because of the eye safety. Yeah. So if this scenario will happen, you may be struggling to read out the distance of the object behind because laser doesn't have enough of power to bounce from the wall back to the sensor. Yeah. LiDAR also very big advantage is there's no problem with the motion blur. You should consider that we need for 1 pixel roughly between 8 to 10 nanoseconds time for acquisition of its distance. So this is so blistering speed that even very fast moving object will not be noticed with any motion blur in your video stream. Yeah. So this is a LiDAR technology, and this technology will be available in our channel, and you can get it from Framos probably in the middle of June and definitely by July. Yeah, so very promising technology, and again, remember, strictly indoors. So very briefly, I will just talk about our camera offerings. I would like to talk so much about it because this is just the tables and some rough numbers. Let me talk about the software now. So I mentioned that inside of our camera is the ASIC, who is processing the whole depth vision. Yeah, it's not causing any payload in terms of the vision processing of the camera. So this is one of the big advantages. So if it goes for software, what you're getting from us is something called Intel RealSense SDK 2.0. It's an open source package. Licensed by Apache 2.0 framework licensing, and this is fully available to you. You get all we do in the form of an open source. What is coming with the interesting thing? The system is capable to fly with any operating system. Even if you will invent your own one and you have a source code from our side, you can create drivers for your platform. And if you go to our GitHub page, you can obviously download precompiled images for Windows 7, Windows and Windows 10 Linux, Mac OS, and Android. Yeah. But if you have something, as a homebrew OS, yeah, you can do something at own as well. Almost any programming language is supported. We obviously trying to do our best in the C++, maybe C#, but also if you're using the Python or Node, JSON, yeah, you can do that. And then this is like the red line, what you're getting from us, and then it's coming the ecosystem. And RealSense is well established as a technology with plenty of third-party wrappers like Robotic Operating System, LabVIEW, Unity, Unreal, and on and on. So then you need to get support from them because we are not originators of this solution. Yeah, we may help to some extent, but this is again for really deep diving discussion with us and with the Framos team. What is it possible to get there? And then also there are third-party software providers where you can get a professional solution for our cameras. Do not expect from Intel to get any middleware or an end-user application as an open source. This is not our plan, and we're not doing it. Okay, so this is to touch the software aspects, and then you have literally two options. You can have a camera as a peripheral. So these are the cameras on the right side in this big rectangular area. And you can also have the modules, and especially the collaboration with the Framos, you can create, almost very rugged industrial solution. I need to say that cameras as branded as RealSense from Intel, they are not targeted for industrial usage. Yeah, we're not claiming any extended lifespan. Yeah, the typical availability of a camera is like 4, maybe 5 years. Yeah, then is coming new generation. And our cameras are not in any form, any IP class of housing. And this is one of the main reasons for our very good collaboration with the Framos in Europe and in North America, that they have the capabilities and competence to create cameras in IP class of housing from IP54 up to IP67. And literally you tell them, that's the way I'm looking to get the computer vision based on a RealSense, and they can do it as a bespoke service for you. Yeah, and this business is usually running with these modules. So modules are another option. You can literally get the components we're using in our cameras and put them into your own housing. Yeah, or into the housing you can get from Framos, which will be validated and certified and tested. So this is on a go-to-market story. I mentioned this self-calibration, so I will not talk so much about it. So this is just the feature of our stereo cameras, that if you are suspicious that the camera is not healthy, you can run in a very fast processes the recalibration on site very fast. And then there's a simplified roadmap, again showing that we have peripheral cameras and we have the modules. It's your choice what you like to use and how to like to use it. And in 2021, we will come with plenty of new products. Even this summer, we're launching another, I guess, 6 cameras. Yeah? So definitely will be a very rich portfolio. You can pick up and match precisely to your needs and to your scenario. My last slide is just to, you will get this presentation from organizers from Framos. So this is a very handy slide showing you the type of a camera, where is expected to use it, yeah, what is the ideal range and environment. Yeah, and I recommend you, when you're starting to consider the technology, start first of all with the environmental questions. Am I going to use it indoors or outdoors or both, and then start to analyze if camera will be matching with other features your scenario. Okay, so so this is in a glance this story of a cameras. And then in the presentation, if you walk slide by slide, you have like one slide review of all technologies on the cameras we selling on the public at this moment, and you can get all these products from Framos, including their excellent support. So this is all from my side related to the presentation. And then now give me roughly 5 minutes to show you very fast what does it mean, depth stream from the RealSense, what you can expect in terms of the precisions, and I will show you stereo, structured light, and a LiDAR camera. So this is roughly just a few minutes to go. So let me run the software. What you will notice that throughout my presentation with the cameras, I'll be running same software without any reset changes. I'm just plugging the camera, run the demo, unplugging, plugging completely different camera. And this is nice showcase that even if you are in a hesitated position, you don't know if you like to use stereo or LiDAR, you can change it over the time without touching your software, because this is completely isolated and the abstraction layer is a very top level. So you can change camera on fly from stereo to LiDAR or to structured light without any problem. Okay, so I will start. First camera will be based on a structured light. So this is this camera called SR300, and camera is connected, will be enumerated over the USB. So now camera is connected, and if I will kick the RGB channel, I have a plenty of compelling, you know, maybe challenging objects, some metallic objects, rubber objects, complex stories. And here is the vision in the depth. Yeah. So what you can see, that camera is a challenging environment, for example, like black surfaces, because this is absorbing lots of laser light. Yeah. Other things you notice in that camera can't see the wall, which is more than 1.5 meters away, because laser can't reach this distance. But camera is very precise for close-up scanning. Yeah. So closer I go, better for me. And I'm operating next to the open window. So if I will close my blinds on the window, yeah, so it's almost dark, then it's a little bit improving the vision of the system. So as I mentioned, camera is typically used in a face identification. So you can see now in a close-up these parallel stripes, yeah, as we're using for coded light. This is slightly scanning my face, and you can see every detail. So if I go into the 3D mode, and you can see me in a 3D, and this is the anti-spoofing proof that I'm the real person. I'm not the photo of someone. Yeah, because if I put my plain hand here, this is a flat, and this is not the face of a person. Yeah, and I can use a RGB channel to create the texture of my face, and I can create on fly, nice high definition 3D model of my face. So this is a structured light camera. Yeah, so be careful on the limitations of a distance. He can't see the wall behind me. You can see the noise. Yeah. So we'll disconnect this one. Let's go for stereo. So another minute for stereo. So stereo camera is connected. I'll be presenting exactly same setup of a scene. So we start with the RGB camera. You can see that this camera is coming with a motion sensor as well. So if I'm moving with the camera, you can read it out if you're building the robotic application. And if you go for stereo cameras, you have a total freedom. You can pick these resolutions. You can change the frames per second of your need. You can check what camera can see in infrared. Yeah. So if I will kick it on, this is the vision from this camera in a stereo. As you can see from this bigger distance, stereo does better performance and recognition in the structured light. Yeah. Because it's capable to better to catch the nuances of the object, and stereo is not suffering with the black objects. There's no problem at all. What is the suffering system is monocolored, unstructured area. So if I'm looking at the desk of my table, you can see that I'm hovering 31 centimeters above the desk. You can see these projected patterns, and here there are no pixels. Everything is unstructured, no diversity, nothing is visible. So if I will switch the laser off, you see the noise. This is a problem for such systems. So if you know that, for example, your robot needs to see and be capable to operate in, I don't know, why wall painted warehouse, you need to have a camera with the active laser. If I bring it back to life, everything nicely visible. Yeah. Structured light camera will be failing looking out of the window. Looking out of the window, you can see the building there, and the building distance is how much? 10 meters, 20 centimeters. So I can look into the sun. I can beam the light from the halogen light, and camera is still performing. Yeah. If I do the same for laser-based system, it will be failing. So this is the structured light. Last bit I'd like to show you quickly is the calibration. So if you think that your calibration isn't accurate, just camera need to see something, yeah, and I go here to the menu, on-chip calibration, I click it, system is doing the calibration process, yeah, it's pretty fast. So basically this is a command you can send to camera, I'm suspicious something is not good, camera will run the health check, camera will tell me this relative value, 22, it says that if I will implement it, it will improve my vision. So I will apply new measurements for calibration. And now my camera is calibrated. And you can see that the depth vision is immaculate. Yeah, everything is running very well. So this is a stereo. Yeah, we're under time pressure, so I need to also give a time to my colleague. So last one is a LiDAR. So LiDAR is connected here. So this is a L515 family of a camera. Because I'm sitting next to the window, there's some light from sun coming, so low ambient. And I will do the same setup like I had with the stereo. So I go for this max XVGA resolution, depth, and RGB. So you see the same scene again. And I go for 3D vision. And I guess you have never seen such performance in a 3D vision. Yeah, so I have an aluminum can, absolutely well visible. If you look in my hand, you can see these small elevations of the skin, like this millimeter elevation, like representing my veins. And actually, I can probably also read out what time is it in a 3D because I can see even the handles on the watch. Yeah, so LiDAR is very precise. But again, what you can see in a certain angles, light is absorbed on the black objects. If I'm looking at the black furniture, I can't calculate the distance. So if something is black absorbing the light, this may be the challenge for this guy. But again, if you're looking such a complex mechanical object, like for example, these Swiss screwdrivers, you know, the precision from the LiDAR is absolutely immaculate. And I think if you're running something indoors, you'll be very happy with the performance. If I open my windows and I'll try to look under the window, you can see only darkness. He obviously can't perform in such light conditions. If I put some strong infrared light, again, he's in the troubles, but it's not the troubles with the LED light. It's not causing any problem. So this is a very brief demo of a LiDAR technology. And I'd like to thank you very much for your time. And I will switch to my colleague, Ferdinand.
Thank you very much, Miro, for your presentation and the kind introduction. My name is Ferdinand Reitze. I'm the product manager for Intel and 3D products at Framos. Miro presented the underlying RealSense technology very well, so I'll put the main focus of the remaining minutes on the USPs of the Framos industrial camera. And we will start with why actually did we at Framos develop an industrial version of the RealSense D435E. At the beginning, we'll talk about our targeted applications, what we learned so far. I'll give you a quick demo of the D435E together with the CubeMOS skeleton tracking SDK that you can also trial via the Intel RealSense website. And at last but not least, we'll have a quick look at our roadmap and what to expect in the future from Framos. So why did we actually choose to develop an industrial grade RealSense? So as Miro mentioned, we also distribute the RealSense product portfolio. And by that, we had already several engagements with customers. And with those customers, we got a lot of feedback and realized and identified three main challenges when using the cameras in industrial environments. For example, the first one would be that when the camera, for example, was installed on an end effector of a robot, the movements of the robot could lead to the disconnection of the USB cables. As a solution, we decided to go for Ethernet connectors and use an M12 threaded connector that prevents the unintentional disconnection. As a second challenge, we discovered that in industrial environments, you may need to position the cameras further away from host PCs. So the challenge is that USB cables are vulnerable to interferences, and sometimes they can act even like antennas when other radiation sources are close by, like mobile phones or microwaves. I wouldn't expect that you have those in your industrial environments, but just for the sake of the argument. And if you go beyond a couple of meters, you would need at least a repeater to overcome approximately 2 to 5 meters with USB cables. By choosing Ethernet and the GIGI protocol, we can now offer cable lengths of up to 100 meters, and we have several customers that use longer cable lengths in their installations of the cameras. Another benefit is longer cable lengths, and Ethernet enables you to leverage networking technology that may be already available. So multi-camera setups from only a few cameras to up to 40 cameras. So we have several customers that use such kind of setups, and that is actually empowered by Ethernet. And the third challenge that we had were that in such environments, in industrial environments, dust and maybe sometimes even spray water is very common. And the open housing of the D435, for example, led to a fast deterioration because dust was able to enter the housing through the cooling slits and sometimes came between the cover glass and the lenses. And we had customers trying to close those cooling slits to prevent that, but that actually led to overheating and was not an option. So this also made sense for us altogether combined to look into an industrial version of the Intel RealSense portfolio, and together with Intel, we were able to realize that. A big aspect during the development was that it's easy to use our industrial version and make it more or less plug and play compatible. So from the start, we made sure that our camera worked with the Intel RealSense SDK. It comes with a slightly modified version, but it allows you to easily switch to an industrial version if you would require it, leveraging the same code that you might maybe have already developed. We also offer some additional features on top of what the Intel SDK provides. For example, you can use an external event mode that allows you to send an external trigger signal either via hardware through the in-output M8 connector or via a software command. And we will also implement a feature that allows you to send a user output signal via the I/O on the M8. So you can, for example, trigger additional lighting equipment to light up the scene if that's required for a specific period of time, for example. Going into the specifics of the cameras, we currently offer two versions, the D435E that has been available since end of last year. And from the beginning of July, we will also offer the D415E. The main difference between those two cameras is the RealSense module that is being used. For the D435, as you can see in the table, it's the D430 module, and the D415 leverages the D410 module. The basic performance, you can compare that to the regular RealSense cameras. So the field of view, the frame rates, the resolutions, all that is comparable to the original cameras. With the GIGI interface of 1 gigabit per second, there are some bandwidth limitations if you want to go for very high frame rates and high resolutions, but that is something that needs to be checked out based on the application and use case. We often learn that the lower resolutions that provide higher accuracy are preferred, and that's why the GIGI interface works quite well, even from the bandwidth perspective. If we go through the explosion view on the left, number one, you see this is a depth module. We right here have the D410 module in our D415E camera. Number two is the RGB sensor, where we leverage the same sensor that is also used in the regular Intel RealSense D435 camera. And three are the connectors. We have two. The first one is the X-coded M12 Ethernet connector. And the second one, the top one, the power connector M8 A-coded, that also includes additional I&O lines. Number 4, we have the Framers PCB. That's where actually everything comes together. To go from USB to Ethernet, we had to design that from scratch. It contains the ISP that receives the RGB stream. It also contains the D4 chip, the ASIC from Intel that does the stereo matching. And we have an FPGA that gets all the information together and translates it into the GIG protocol and transmits it via the M12 out. Number 5, the IP housing. We can offer by default the IP66 housing, but we also have the possibility on a project basis to provide IP67 housing. Those require a different ceiling, so that will add a little bit up on the costs, but in general, this is possible. And we also demonstrated that already on the trade shows where we had a D435E underwater for 4 days working without any issues. We also are able to offer a modular version. So if, for example, you want to design in the camera and you have no need for such a IP-rated housing, or if you have such a housing already by yourself, that would include just the depth module, the RGB module, the interposer cables, and the PCB. But we can basically offer also the glasses or maybe the mid plate that you might want to use. Actually, this one is quite important. It's the plate where the modules are mounted on for the heat dissipation. Heat dissipation is actually one of the reasons why, from a dimension perspective, our camera is slightly larger than the original RealSense cameras. We have 100 millimeters in width, 47 millimeters in height, and 38 millimeter depth. I will show you a comparison in the live demo so that you can have a visual. And the main driver for the additional weight that we have also in the camera of 250 grams roughly is, as mentioned, the mid plate, because it's required. We don't have any cooling slits, so the heat that is developed mainly by the laser projector, if it works at full power, for example, to get that heat away from the modules and move it towards the outside of the housing. So when you use the camera, obviously it will get quite hot. For the mounting, we offer 4 times the M3 holes. Those are the same mounting options as you have with the RealSense D435 and D415 cameras. To add more on to the ruggedized version, we have 4 instead of 2, and the camera should be mounted on a heat conductive material to ensure that it can work properly in the specified operating temperatures. As for targeted applications, we learned with our customers that in general the application and areas of use are areas where you expect a lot of dust, maybe spray water, or where you would require a rugged camera from the start. This could be, for example, if you want to mount it close to the ground in a production facility. Another thing is where it's very useful is when long cable routing is required. We had or have a couple of customers that started with the D435 or D415 in robotic automation, and they added mini PCs close to the camera that then enabled them to translate to Ethernet from USB. That not just added up to the cost, but also made the full setup more complicated. Using Ethernet and long cable option is definitely simplifying that setup. In typical use cases, there's quite a large overlap with what Miro already presented in his deck at the beginning. Real-time automation, object, people recognition, counting, or monitoring. We target the industrial automation, logistics, and even precision agriculture or mining applications. Now to a very quick demonstration. I will switch over and start our CubeMOS skeleton tracking SDK. This is directly connected to the D435E, and in a few seconds you should see me live. There we are, and as you can already see, my body is directly matched with a skeleton and a couple of joints. In total, up to 18 joints are possible by the software SDK, and it makes a very fast and simple way from an image to go to human pose estimation. So let me very briefly show you. Right here we have the D435E camera and the original D4. Let me move it a little bit to the side so it's easier to see for you. The original Intel D435. So as you can see, it is slightly larger, but in general the form factor is still quite small compared to other options in the market. The SDK actually uses the 2D image to figure out the joints, and then uses the depth information from the camera to assign the coordinates. And this is a very interesting and very fast tool. And let me show you a quick demonstration so you can see how fast this software works. So I'm just holding up my cell phone with two people running next to each other, and right away the SDK recognizes the skeletons. And even if I move, it tracks the people correctly. There are some interferences with the reflections because the sun changed, but I believe it still shows you very, very nicely how this works. As mentioned, this SDK can be acquired through the Intel website, or if you reach out to any of our sales representatives or FAEs, they can also help you with that. Now, to close up, and before we go into the Q&A session, a quick look at the roadmap. We already implemented a lot of new features over the past releases. The next one will have a focus on adding an additional wrapper. So the RealSense library, the SDK, the modified version from Framers will also be able to offer LabVIEW wrapper support. We are currently developing and implementing RGB and depth synchronization for single camera setups and support for hardware timestamps. Those two are mandatory to offer the dynamic depth and RGB calibration in a later release. So as you can see in the upcoming section. And the next release in July will also offer the option for sending a user output signal over the M8, as mentioned, to trigger an external event on a different piece of equipment. And obviously it will also have the full support for the D415E camera. We work on additional features like enabling the IMU that is integrated on each of the cameras, both the D435 and D415E. We want to add multi-cam synced hardware and software trigger options for the external trigger event, and more continuous improvements enabling more of the features that come by default with the Intel SDK. Thank you very much for joining this webinar. And now we are off to the Q&A section.
Perfect. Thank you so much, Miro and Ferdinand, and thank you to all who've stayed on with us throughout the duration of this webinar. Just to say, if you haven't submitted your questions yet, please do so now, and I'll try to get to them. We have a long list of questions that I do want to touch on. So, Miro and Ferdinand, please get ready for your first question. So the first one says, regarding the Intel RealSense LiDAR, are you also working on LiDAR which works outside, in brackets, sunlight/daylight, for instance, like the new Apple iPad LiDAR?
Yeah, this is Miro speaking. Yes, we're working on an alternative to operate outdoors, but this is a classified information. I can't comment any more to that. By the way, the brand mentioned is not running real LiDAR, just to be technically correct.
Okay. That's good. Another question is kind of the same in its sense, where it says LiDAR failed to work in cases like lawnmowers. Is it because of the distortion from the sunlight? What would be the solution for outdoors? So I think this ties in with the question before. So you want to take a stab at it?
Yeah, I can answer that. So at the moment we're using 860 nanometer spectrum of infrared lasers. So these are the flashes in 860 nanometers. This is, you know, very much influenced in the case of ambient sunlight. An example, if you look in the data sheet of a LiDAR, which is a public information, so ambient light intensity as a sunlight should not exceed 500 lux of intensity of the light. Utilizing similar technology outdoors means that we need to change the spectrum of a laser.
Okay. The next question is, will it be possible to use an external trigger signal with synchronized depth and RGB sensors? Is this one you want to answer, Ferdinand?
This is.
Is it for the D400E series or the regular?
It didn't specify. It just.
If it's an external trigger, I would imagine that it relates to one of the last pieces of information that I provided. Yes, this will be possible. With the next release, we will implement the depth and RGB synchronization for single cameras, and if everything allows it, we will try to release the functionality for the external trigger and hardware, software and hardware event already by then, or at the latest with the release after for Q4.
Yeah, just the other from my side is the engineering, and also on every recent camera, you can see on a housing there's something like SIM card slot. Yeah, but this is not for SIM card indeed. This is just the connectivity pin for I2C chip interface to ASIC inside of the camera, when you can read out the timestamping signal from the ASIC, you know, so then you can synchronize almost any other RGB or other camera with our Wilson's camera. Yeah, so it's just with the matching. This is a trick behind, also utilized by Framos in the synchronization of RGB channel with depth.
Okay. The next question is, I would like to design the D435E into a product, but do not need an IP66 or an IP67 grade housing. Is the D435E available as a module or embedded vision?
Yes, it is possible. So if you would require that, please reach out to your sales representative at Framos or the FAE to get all the information that you require. So basically, it would contain the depth module, the RGB module, and the interposers that you need to connect to the Framos PCB. Apart from that, everything else that we can offer is not mandatory, but so feel free to reach out, and we'll provide you more information on how that would work.
Okay, perfect. And I'll do one more question. As I said, there's a lot to get to, and I have to be cognizant of other people's time as well. Just one more question, and then we can wrap up. It says, does Framos consider making an industrial version of the L515?
We are looking into that. As you've seen so far, no module version of the L515 is announced. So we work with Intel on checking what is possible based on the L515 camera. We are quite interested to make that happen. So we are in evaluation phase on that.
Okay, perfect. I'm going to wrap up right now, as I think we've gone over our time, and I want to be, as I said, cognizant of other people's time. Thank you so much, Ferdinand, and thank you so much, Miro. I think it was a very impressive presentation today. You've both delivered quite well, and I think we're quite happy, and the audience is quite happy. But just to reiterate to the audience, we will send the slide decks as well as the question and answer and the on-demand version of the webinar to you in the next few days, so keep an eye out on your inbox. Our next webinar will be in a couple months, so stay tuned for your personal invite. And if you do need to get on our mailing list, please let us know. We'll add you as well. Also, please follow Framos and Intel RealSense on LinkedIn and Twitter for company information, product launches, webinars, and all virtual events that are happening in 2020. Once again, I want to say thank you so much for staying with us, and we appreciate you, and we'll see you next time. Bye-bye.
Goodbye.